Okay, this is a uh, study of the homework examples for Conceptual Physics Chapter 4. Um, Before we get into problems, just a brief discussion of what we have learned in this chapter, and it's Newton's second law of motion. The acceleration is directly proportional to the applied force, is in the direction of the applied force, and is inversely proportional to the mass. And we write that in equation form that acceleration is equal to the net force, that's the sum of the forces, divided by the mass. Now, force is a vector and acceleration is a vector. And whenever you multiply or divide a vector by a scalar, you're going to get a vector in the same direction, but just modified by a factor. So we have a force in a particular direction. The acceleration is going to be in the same direction, but just modified by the division of the mass. And you notice that the force is in the numerator, so if it increases, the acceleration increases. The mass is in the denominator, so if it increases, the acceleration decreases. If the mass decreases, the acceleration increases. It's inversely proportional. Now, we have another way of expressing this, and that is that the total force, the sum of the forces, is equal to mass times acceleration. Now, weight is a force. It's a downward force caused by gravitational acceleration. So we use this form of the equation when we calculate weight. Weight is equal to the mass of what we're weighing. This too many bumps. Mass times gravitational acceleration. And here we use gravitational acceleration of 10 meters per second squared. It's actually 9.8. We don't introduce that big of an error if we go to 10 meters per second squared. Okay, so that's kind of your cheat sheet for this chapter. There's not many equations. It's not like, well, we had the equations of motion in the a previous chapter. In fact, we're going to use one of those equations. Let's look at this problem. The human body can withstand an acceleration of 10 grams, not 10 grams, 10 G's. 10 G's under certain conditions. Well, what's 1 G? 1 G is 10 meters per second squared. So 10 G's is 100 meters per second squared. The human body can withstand an acceleration of 100 meters per second squared under certain conditions. Well, what net force would produce this acceleration for a 50 kilogram person? Well, first, let's look at what might cause it. And here in San Antonio, Texas, we have a human centrifuge. You read the caption, it says KBR Weil has operated and maintained the Brooks Centrifuge in San Antonio, Texas for more than 50 years. This is where we train our pilots to withstand the kind of G forces that they come when pulling a jet through very tight circles. If they're not careful, they pass out and they could conceivably crash their airplane. So they train them how to counteract the strong G forces. You can look it up online, look it up on YouTube, and say centrifuge training for pilots, and you'll see that there's some that do indeed pass out at like 9 G's. I think there's one that even passes out at 7 G's. It's a lot. That's a lot of G's to be experiencing. Anyway, let's get back to the problem. That's just a little aside. I thought it was interesting that we had that centrifuge here in San Antonio. Okay, the human body can withstand an acceleration of 10 G's under certain conditions. What net force would produce this acceleration for a 50-gram person? So we're going to use this, the sum of the forces, the net force equals mass times acceleration. So we want to know what is that net force that would cause a 50 kilogram person to experience 10 G's, which is 100 meters per second squared. And we'll see that it's 5,000 kilogram meters per second squared, which is a Newton. So it's 5,000 Newtons. So there's your answer. There's your answer here. Okay, 5,000 Newtons. Okay, now let's go on to another problem. There's the centrifuge. Let's say a 2,000 kilogram car experiences a braking force of 10,000 Newtons and skids to a stop in 6 seconds. The speed of the car just before the brakes were applied was, and then you have to calculate how many meters per second. And it's like, wait a minute, Mr. Menchaca, there's no velocity in any of these equations. You're correct, but we can get it nonetheless. So let's look at what we know. We know a mass and we know a force. So with that mass and with that force, we can calculate an acceleration. The net force, the braking force, is 10,000 Newtons divided by a mass of 2,000 kilograms. So the acceleration is 5 meters per second squared. Okay, 10,000 divided by 2,000 is 5 meters per second squared. Okay, now from the previous chapter, we know that acceleration is also defined as the acceleration is equal to the final velocity minus the initial velocity divided by the time. Okay, well, we know that the final velocity in this case is equal to 0. So that's going to come up with the acceleration is equal to V initial, there's my V initial divided by the time, which means that the V initial is equal to the acceleration times the time, which in this case is the acceleration is 5 meters per second squared, 5 meters per second squared times 6 seconds. And we're going to get 30 meters per second. And if we look up here, that is the correct answer. Okay, so even though one of the reasons I chose this problem to demonstrate is because physics builds on itself, or at least the way we're studying the physics, it's going to build on itself. So you learned something about the equations of motion in a previous chapter. Doesn't mean, okay, you satisfied it for that chapter, you can forget them. No, we're going to keep using those. And here's a demonstration of how we're using those equations as we continue to learn our physics. So that's something to keep in mind, that physics is going to build on itself. But that brings us to the end of this little homework demonstration. I hope this helps. And we'll end the lecture at this point. All right.